নমস্কার। অলরেডি দুপুর হয়ে গেছে, তো আই এম gonna quickly switch to English so that all of our speakers and audience feel included. So yeah, today we are gonna be talking about improving Beam data flow pipelines for text data pre-processing. How many of you are working with NLP, by the way? Like applications that include a lot of text data? Even if you are not, I hope my session is going to be beneficial and helpful for you because we are going to talk a lot about distributed computing and stuff like that. So yeah, let's get started. So here's what I do, sort of shamelessly reintroducing myself. An ML engineer at Carted. I work with NLP data and also a lot of raw HTML data. I have a flair for open source stuff. I have contributed to Keras, CV, Hugging Face transformers, and so on. And of the work, I really like to watch things on Netflix. And currently, I'm trying to complete Peaky Blinders. So by the order of Peaky Blinders, let's get started. All right, so a disclaimer, I'm presenting this work on behalf of my colleague Nilabhro and myself. So yeah, please keep that in mind. Okay, this is how we are gonna do this. We are gonna first walk through the problem statement, then all the tools that we will be using, then I'll be walking you through the unoptimized pipeline and the things that could have been improved in the unoptimized pipeline. And then, of course, I'll be sharing recipes by which you could optimize your data pre-processing pipelines. And of course, I'm a numbers guy, then we will get to the results. All right, problem statement. So pretty simple stuff. We want to generate text embeddings. And as Shweta was mentioning, we want to, generate some dense text representations that can be useful for other downstream stuff like, search relevance and so on. So our goal is to generate text embeddings. Pretty simple. So we will take text comprising of multiple sentences as inputs. Then we will tokenize the sentences into words. And then we will generate text embeddings using something called a sentence condition BERT model. That's not the important part here. We are not going to be talking about model training today. We are focusing on data pre-processing, so yeah, we can ignore that part. But the simple problem here is to generate text embeddings, but at scale, at a billion scale, let's say at an internet scale, okay? So yeah. So let's take a quick look at the tools. So we will be using BigQuery for receiving the inputs. Then we'll be using a Python library called sentence splitter for splitting a piece of text into sentences. Then we'll be using a tokenizer and an embedding model from TensorFlow Hub, the sentence condition BERT model basically, which is the very least relevant part here. And then we'll be using Apache Beam to pack our different data pre-processing steps into a pipeline. And then we'll be using Cloud Dataflow. This is a GCP event, come on. So we'll be using Cloud Dataflow as our pipeline runner. And I'll be talking about why we are using Apache Beam in a moment. And of course, we'll be using cloud storage for saving our artifacts. So here we go with the unoptimized pipeline. So yeah, we'll be reading our data from BigQuery. Then we'll be pre-processing the text using a pre-trained tokenizer. And then we'll be generating text embeddings with a pre-trained model. And then we'll be finally serializing those embeddings as binary strings. And then we will write them as TensorFlow records to a Google Cloud Storage bucket. Pretty simple stuff. And we'll be using TensorFlow, Apache Beam, and Cloud Dataflow for this. And in terms of code, you don't need to, understand a whole lot of Apache Beam. Just focus on the simple bits here. We are first reading stuff from BigQuery. It's a simple SQL query. Just select star from whatever. And then we are tokenizing and embedding the text descriptions. And remember that we are doing all of that into a single Purdue step. And then we are basically, converting the extracted text embeddings to binary strings, and then finally we are writing the binary strings as TensorFlow records. Now, I want all of you to remember this step. Like we are tokenizing and embedding all the text descriptions in a single step. Now, I'll come to the implications of that in a moment, but just remember this for the time being. All right, so what can be improved? Any guesses? I'll just take one or two inputs. Like this is our initial pipeline. What can be improved here? Go ahead. Why?
Step. So if hello. So if I am doing these two steps in a single step, so it might happen like tokenization can fail, and after that embedding can also fail.
Why would tokenization fail in the first place?
Like I thought about
Let's
that.
say all of that is ensured. Are there any problems? Let's say we have, taken all the measurements, all the nitty-gritty tests. We have taken care of all that.
Okay, that I don't know.
Cool.
Sorry.
Anyone else? I'll just take one more input. Yeah, go ahead. Ayush.
Yeah, so I don't know if this is parallelized, but if it's not,
Apache Beam works with
Okay.
parallelization by default.
then I don't have an answer.
Okay, cool. No problem. No worries. So I'll stop there. And again, we are using Apache Beam because these kind of pre-processing, they can be applied on a row by row basis. And as long as you have some methods that are independent of each of the rows that you are dealing with, then you can pretty much vectorize or parallelize anything in the world. If the rows are not, dependent on each other, you can parallelize all of your, utilities. Okay, cool. So what can be improved? Let's get down to business. So we are using a sentence condition BERT model, and it can support a maximum sequence length of 512, right? And if we use a global sequence length of 512, think of the computational waste that we will incur, right? Let's say we have a in a batch we have a sequence length of, let's say, maximum sequence length of 4, right? And if we are padding those sequences to the sequence length of 512, we are essentially padding what? 508 zeros to a sequence length of 4. And that's a lot of computational waste. And we can save it, and we can use other stuff in order to optimize these things. I'm going to come to that later, but if we use a global sequence length of 512 rather than using some sort of other modern strategies, then we are going to lead to a lot of computational wastage. And we would want to avoid that. And of course, I wanted all of you to take note of this. We are doing, we are performing tokenization and embedding extraction in the same step. And why this is not good? Let's see. So tokenization is fairly a CPU-bound process, and it does not benefit from CPU instructions like AVX 512 and so on. And AVX 512 happens to be a very optimized instruction set, which can benefit parallelization, and tokenization does not benefit from that. And on the other hand, computing embeddings from the padded text sequences, it benefits from vectorized operations. And if we do tokenization and embedding in the single step, the embedding utility will have to do it for single examples. And I just mentioned it benefits from vectorized operations. So it means that if we throw a batch of text sequences, it will benefit. It will, optimize the computational performance. But here we are only throwing single example at a time. So again, it will lead to a lot of computational wastage. And we can clearly see that tokenization and computing embedding, these have contrasting computational requirements. So naturally, contrastive things will lead to computational wastages. So yeah, let's see how this pipeline can be improved. All right. So instead of using a global sequence length, what if we could take a batch, compute the maximum sequence length within that batch, and do the padding according to the batch-wise maximum sequence length? The concept is pretty simple. On the left-hand side, we see 42 white squares, which basically denotes the positions that need to be padded. And on the right-hand side, if we do the batch-wise sequence length padding, then we only have 36. So just in a moment of time, we were able to reduce the number of zeros down to 36 from 42. So of course, this is a very tiny bit of improvement, but we can do a whole lot. Let's see how. So if we take the sequences, a batch of sequences, and sort them in a non-decreasing manner, now we can see from 42 white squares, we are now down to only 11. From 42, we are now only down to 11. So what we are doing is, we are taking a batch of text sequences. We are then sorting them according to their sequence lengths in a non-decreasing manner, and then we are further chunking them, and then we are applying the whole thing. So first you apply sorting, then you compute the sequence length with respect to the batches, and then you do your truncation padding or whatever you want to do. Cool. This is also referred to as smart batching, by the way, in the PyTorch community. So yeah. All right. And I also wanted you folks to remember that we are performing tokenization and computing embedding all in single step, but we can pretty much break that single step down into 3 separate steps. So first, we will be doing the tokenization. We'll be first tokenizing all the sentences in a single Purdue step. Again, this is a very Beam-specific terminology. And then we will apply batching. So if we do not apply batching, then we will have to wait for the pipeline to complete all the tokenization of all the sentences. So that's why we are doing batching first. And batching has an advantage. So if you use the batch elements operation from Apache Beam, so it has an advantage. So if you provide it with a range, let's say I want to keep my batch size from 5 to, let's say, 200, it will intelligently adjust the batch size of the pipeline so that the pipeline does not get overhauled, right? So it will make sure all the memory utilization, all the CPU utilization, all of those things are in check. So yeah, the second step would be to sort of batch all the elements after they have been tokenized. And then we do the following. Then we sort of collect all the sentences. Then we sort them. Then we batch them together. Then we compute the embeddings. Then we unsort the embeddings. Then we go with the rest of our pipeline. So this is how the code will look like. So again, pretty simple stuff. We are reading things from BigQuery. Then we are tokenizing things. Then we are batching things. Then we are performing a utility called embed examples, which takes care of the sorting. Again, batching, and then, of course, computing the embeddings. And then it will finally unsort the embeddings to make the representations or the extracted embeddings meaningful enough for the downstream steps to be consumed. All right. Let's get down to the results. Probably the most interesting part. So, we are dealing with some 22,000 examples. So the total, generated examples will be in some 13 lakhs. So the maximum number of workers that we used in Cloud Dataflow were 500. So let's say we imagine 500 different computers working in parallel. We used some N1 custom machine type, again very GCP specific. And our measurement was the wall clock time. So with respect to the wall clock, we measured the efficiencies of the different experiments that we tried of. So the unoptimized pipeline, the wall clock time was 3 days, 11 hours. When we decoupled the tokenization and the encoding step, like first perform tokenization and then perform the computing embeddings. When we decoupled that, then we were down to 3 days, 5 hours. Again, not much of an improvement. So yeah, after we started, sorting the, what happened? Oh, we are back, thankfully. So after we started, sorting the batch of sequences, then we were down to 4 hours from 3 days. I think that should raise a few eyebrows. Yeah, from 3 days to 4 hours. And then, after we, collated all the stuff that we just discussed, we were down to under 3 hours. So from 3 days to under 3 hours. Okay, so it's like from $5,000 to under $100. So, yeah, and we can do more. Doing more. Okay, let's do more. Since we are dealing with a neural network here, and since we are using CPUs, we can pretty much optimize any neural network with something called ONNX. So we optimized our sentence condition BERT model using something called ONNX. And we used, compute optimized hardware, which has things like Intel Xeon 3rd Gen, which are known for, known to run deep learning workloads in a very optimized manner because they have the instruction set called AVX512. So now we are down to under 2 hours. So 1 hour, 48 minutes. So that kind of concludes my talk. If you want to check out the resources, we do have a blog post around it. We have open source all the code that's needed for you to get down to under 2 hours. So feel free to check that out. And if you want to ask any questions, I'm all ears. Any questions? Go ahead. We have 4 minutes left. I think I can take 4 questions.
Hello. Yeah, so
What's your name?
Yeah, I'm Bhashwati Roy.
Hi.
Hi. So can you just explain global sequence length in a detail and how is it related, like with some examples in that?
For sure. Let's say this is Taj Kutir, this is a sentence, this is Taj Kutir. This is Newtown, this is again a sentence. We are living in Calcutta, this is again a sentence, right? Now, by sequence length, I mean number of unique words in a sentence. So this is Taj Kutir, this is what? 4, sequence length of 4. We are living in Kolkata, this is sequence length of 5. So if you consider a data set of 2 sequences, having we are living in Calcutta and this is Taj Kutir, what is the global maximum sequence length? 5? Yeah. We are living in Kolkata. Now imagine having a data set where we have multiple such sequence lengths, 23, 25, 26, 30, 100, 512 or whatever, right? Now, you calculate the maximum sequence length in the entire data set. That is your maximum sequence length. Now, consider operating with batches of text. Now, in a batch of text, 512 might not be your maximum sequence length, right? In that batch, it could have been 23, it could have been 100, it could have been 512. So would you want to use a maximum sequence length of 512? Would you want to pad everything to 512? You would want to use the maximum sequence length of the batch that you received, right?
Yeah.
That's the idea.
Okay. So can it extend 512? I mean, it can be more than that also.
If it's more than 512, then you truncate. Then you cut things off.
Bring down to 512 again.
Bring down to 512.
Okay,
Exactly.
okay. That answers my question. Thank you.
Go ahead. Now I'm gonna show this, from 3 days to under 2 hours. I'm gonna take a lot of pride in that. Yeah.
Hello, sir. My name is Sobik. So my question is, how many different types of tokenization are there?
There are lots of tokenizations, like Shweta mentioned about TF-IDF. It's just a way of representing text. So we use something called unigram. There's sentence piece, there's word piece, there's byte pair encoding. We used unigram. So there are 4 or 5 different types of. If you go to huggingface.com/tokenization, you will see all the different kinds of tokenization that are out there. Cool.
Sir, you give us the blog. Can I find different types of tokenization there? The blog.
Yeah, in the blog post we do mention a couple of tokenizations that we tried out. But if you have more questions, just feel free to open an issue thread in the GitHub repository, and we'll be more than happy to answer.
Okay, thank you, sir.
Yeah, Rishiraj.
Yeah, so I wrote down my question. You mentioned in your slide that we are sorting before batching, but why? You can open that slide as well. So we are sorting before batching, but why use that? We can use these batches of with sequence of same length, and then we can use something like a BERT encoder. So why sort before?
Yeah, so the sorting helps with CPU instructions. So if your CPU is focusing more on higher order stuff, then it has an advantage. If you are throwing random stuff to it, it won't be able to accurately approximate, hey, this is how I route this instruction, this is how I route this instruction. So if you guide it toward processing, processing sequence lengths in a non-decreasing manner, it will be able to better route its instructions.
Okay.
So it's very low level stuff. So I am glad that you asked this question.
Fine, thanks.
Cool. But yeah, there's one catch. You wouldn't want to sort sequences when you are training, because that way your model will get overfit to that particular pattern. That it will think that, okay, I'm going to expect 512 first, I'm going to expect 128 first, I'm going to expect 26 first. Never do that during training. Cool? Cool. $500, by the way, for that tip. Go ahead. We have only 30 seconds left, so.
Hello. Am I audible?
More than enough.
Okay. Thank you for giving me the chance to ask the question. My question is, can a batch have variable length entries?
Yeah, absolutely. That's what we did here, right? So
Yeah.
your batch, yeah, go ahead.
Is there any limitation how many we can have?
It depends on the maximum sequence length supported by the model that you are using. So here we used BERT, but for models like Big Bird, it has a maximum sequence length support for 2048. So it depends on the kind of model that you're using. For BERT, it's usually 512.
Thank you.
Cool. Anyone else? Go ahead. Can we have a mic here? Yeah, just one more question. Cool.
Yeah, actually, already Rishiraj asked some kind of similar question, and you already answered, like the sorting and non-sorting part. So I was just wondering, like, as you were saying that you have large-scale data, so traversing through all the data, like if you do not have the metadata, isn't it like I can understand the reduction in training time and everything. So, but I'm curious about how much overhead it is happening for the sorting and unsorting for the whole data from when you have cloud storage and NFS.
Absolutely.
Yeah.
So that's why we are using batching before it. So we are tokenizing everything at one go, then we are batching, then we are sorting things. So we are taking a batch of data, then we are sorting only that batch, then we are applying another batching in order to sort of collate things, then we are applying embedding. Then
So you sort the whole thing
no,
first?
we are taking a batch. The second substep is batch.
No, there was one thing like when you drop to 11, 11 free spaces, like you had a slide. I think I just saw, right, like
This one?
not this, before.
Before?
It was in early,
This one?
no, before that. Yeah, this one. Like this smart batching, like you sorted everything in decreasing order and then batched, right?
Yeah, so we are only operating in that batch only. Consider having received that batch only.
Okay. That is not, okay. Yeah, got
So
it.
we are using multiple systems, no? So every system is operating on their individual batches.
Okay.
So that's why it's possible.
Otherwise, it
Absolutely not.
Yeah,
We
so-
can't think of
the overhead would be very high. very high.
Yeah, that's why distributed processing, because all the rows are independent of each other. That's why.
Thank you. Yeah.
Cool. Anyone else? Just one more question, maybe? One more? Cool. Go ahead. Lots of questions. Cool. Go ahead.
So, what is the AVX 512 instruction set? How is it different from other instruction sets?
So AVX 512 is a specialized instruction set that can benefit parallelization, right? So neural networks, the bread and butter for neural networks, I think, are matrix multiplication and a couple of additions, right?
Yes.
So matrix multiplications and additions, these operations can be largely vectorized. So AVX 512 helps with vectorization. And since neural networks happen to be, vectorizable machines, that's why AVX 512 helps. And other instruction sets like AVX2 or the vanilla AVX, they do not have that support for vectorization. That's what.
Okay, sir.
Cool. One final question? Anyone else? Go ahead. Hello.
Hi, so my question is, if there, for example, we are taking a batch of 10 sequences, and then a sequence of highest length, for example, 512, and sequence of lowest length, for example, 1, will they be in a single, can they be in a single batch?
If you only have a batch of 10 examples and you happen to have that statistic, probably it's very unfortunate, but in the first place, you would want to, cancel the sequences that have that have a sequence length of 1, because they're probably garbage. Because if you already know that your average sequence length would be, let's say, 128 or 512, then having a sequence length of 1, the sentence isn't meaningful. So yeah, I mean, if it so happens that in a batch you have a maximum sequence length of 512 and the lowest sequence length is 1, then wait.
But it can happen, right? If we are not
It can
sorting
happen.
before batching.
Yeah, it
then
can happen.
This
It can happen.
situation-
That's why exactly.
Yes.
That's why exactly we sort.
Okay.
Cool. I'm done. All right. Thank you, folks.